We were working on variation of parameters and trying to solve this particular problem. Non-homogeneous, the right-hand side is not our nice um, functions, one of those four basic functions. And so we're going to need to use a different method from undetermined coefficients, which is variation of parameters. So let's say variation of parameters. And then the first thing we need to do is we need to solve the homogeneous version of this. So I think that's where we started. So we have the triple prime plus the y prime is equal to 0. And then you find your auxiliary equation, m cubed plus m is equal to 0. And then if you factor out an m, we're going to get m is equal to 0 as a solution. And then we got to get complex numbers. Because we get imaginary numbers. And so your solutions, let's say y1 is equal to e to the 0 power. And your y2 is going to be a cosine of 1 times x. There's a real part of 0 here, so that's e to the 0 times sine and cosine of 1 times x. And so that's our complete set of solutions. And then from here, we wanted to work with finding our Wronskian, and then using Kramer's rule, finding 3 more Wronskians, or determinants of Wronskians. So our first main Wronskian is going to have a 1 cosine x and a sine x, and then its derivatives. And we're going to involve the third derivative here. This is a third order differential equation after all. So the derivatives of constants are just going to be zeros. The derivative of cosine is negative sine, and then one more derivative is back to negative cosine, then all this other stuff. And so to find the derivative of 3 by 3 matrix, we're going to expand on a particular row or column. And I would probably encourage you to try to expand on the column that has the most zeros. And so since we have a 0 everywhere else, those are not going to contribute anything. And then we just have a submatrix that we're going to compute. And we know how to find determinants of 2 by 2 matrices. So our determinant of W, I guess they call it W, determinant of the matrix, is going to be 1 times the determinant of the submatrix that's left over after you cross out the row and column, minus, and then remember you alternate pluses and minus, 0 times some other matrix that I'm not going to care about, and then 0 times some other submatrix that I'm not going to care about. But if you know those are non-zero, then you'd have to make sure you find those matrices. In any case, we have sine squared minus negative cosine squared, so that's just going to be a Wronskian of 1. Okay. So now let's find, we're going to need 3 of these. We're going to need W1, W2, W3. Let's see if I can make it all fit into one row here. So our f of x is equal to tan x. And so our Wronskian 1 is going to be the first column replaced with 0, 0 f of x. and then the other two columns will remain the same. So we got cosine x, sine x, minus sine x, sine x, minus cosine x, minus sine x. So if we figure this out, again, expanding on the first column, we can say this is a positive, a negative, and a positive. So we have a 0 times some matrix minus 0 times some other matrix plus tangent times the submatrix of the tangent that's left over, which is this cosine sine matrix. Cosine x, minus sine x, cosine x. And that looks like it's going to be 1 again. So our W1 is going to equal to 1. That's nice. So our W2 will keep the first and third columns the same. And then the middle column, the second column, is the one that's going to change to 0, 0, f of x. And here you can expand on the first or second. It doesn't really matter. So I'll expand on the first because there's a 1 in there. So there's a 1 times the submatrix 0 cosine x, tan x minus sine x. And so that's going to be 0 minus negative tan x cosine x. Yes, tangent is sine over cosine, so let's just call that minus sine x. Okay. So that's 2 down, 1 to go. Our W3 is a 1, 0, 0, cosine x minus sine x minus cosine x. And then it's your third column that needs to change. And again, I'll expand on the first column. It's going to be 1 times sine x, 0, minus cosine x, tan x. So in this case, I will have sine x and tan x. That, for now, I'll leave like that, and then we'll mess with that later on as we need to. Okay, so far? All right, well, because W, the original W is equal to 1, our U's are just going to be these W1, W2, our U primes. So that's let's get our U primes, and then we'll find antiderivatives. So the derivative, or our W1 is 10x, and then our W is just equal to 1. So this is all we have, which will get us to our U by integrating tangent function. And I think this is equal to some ln and secant and something like that. Look it up. Is it negative? Yeah. Yeah, you could. Then that kind of defeats the purpose of. Yeah, but then you lose a third order. We're doing a third order example for that. No, I meant we're doing this to practice 3. That's not to make you suffer. Just to give you practice for third order stuff. So what's U2? I think that's a cosine. And it looks like we need to integrate. Didn't we run into this before? Sine x, tan x. So secant x minus sine x. And then again, those formulas that you should, or something. If you guys tutor Calc 2, you just integrate all the time. So if you just, or you could just integrate all the time on your own. Just look at some Calc 2 worksheets. I have some integrals that you guys can work on if you want practice. I suppose I could. So the integral of secant is, I think we did that. No, we didn't do that. It's ln of secant x plus tan x minus integral cosine, positive sign. All right. And then from here, we string them all up. Our y particular solution, we'll call it y sub p, is going to be equal to y sub 1, or u1 y1 plus u2 y2 plus u3 y3. So it'll be 1 times ln of secant x plus cosine times cosine, because we have a cosine for u2 and we have a cosine for y2. And then here we have sine x times ln of secant x plus tan x minus sine x. And people sometimes put this together and say, oh, that's a negative. Never mind. I was going to say if it was a positive, it'll be cosine x plus sine x, and then, or cosine squared x plus sine squared x, which is equal to 1, and they get rid of it. But it's a negative, so if you punch this into Mathematica, they might use some other double angle formula or something. So our general solution would just be the solution to the homogeneous part plus this particular solution that we found. So it'll be 1 times C1 plus C2 times cosine x plus C3 times sine x plus all the rest of the stuff here. Okay. So anything that seems confusing in class, you should go home, write it out, get a whiteboard, write it out. Make sure you understand the step-by-step process. These little integrals, little integrals. that may not seem obvious, make sure you look it up and actually see the formula in the table to make sure you're familiar with it. Because the more you do that, the more you'll get familiar with it, and then the more you're familiar with it, the easier this is going to run through your head, especially like taking the when you're taking the test and you're trying to freak out and trying to figure out what the integral of something is. If you do enough of these, you get familiar with it and just say, oh, that looks familiar. And then you'll have the table on your sheet of notes. Say it again. Oh, we're not doing any row swaps or anything like that. We're just finding determinants of stuff. Anything else? Okay. All right. Let's move to a different kind of, slightly different kind of differential equation. The differential equations we've been dealing with have constant coefficients. They've been nice and stuff, but not everything is going to be like that. So we're going to see another type of differential equation that does not have constant coefficients, but it follows a certain pattern, and the certain pattern makes it a particular type of differential equation. And so these are called Cauchy Euler differential equations. And if you look at the Cauchy Euler differential equation, you see that it no longer has just regular constant coefficients, but the coefficients have to be special in the sense that they match the order of the derivative that they're multiplying, the powers. So these are power functions next to each of these derivatives, and the power functions match the number of times you took the derivative. Okay. So this is a Cauchy Euler differential equation. Now the first thing we're going to do is we're going to take a look at the homogeneous portion of this, and then after that we'll apply Green's, or not Green's theorem, or apply we'll apply the variation of parameters to solve for the differential equation, the non-homogeneous. Greens. Yeah, it's in my notes too. We'll get there. So, how we're going to solve for this? What we're going to do is we're going to, like I said, consider the homogeneous portion of it. But for the constant coefficients, we assumed that we had our solutions to be of some form, and the form was like e to the m times x. And so now we're going to change the form on you a little bit, and you just have to remember that when you're dealing with a Cauchy Euler differential equation, your form is going to be x to the m power. It's a power function. And it kind of makes sense because you're matching the derivatives here with the power function. So we'll have x to the m. Now, just like the other case that we had, we're going to run into special cases because I think we're going to run into the quadratic formula, quadratic equation again. And so We can list down the cases and then do some examples, or we can do some examples. Why don't we try to do a generic example? And let's work this out for a second order differential equation. And we'll generically put A, B, and C as some arbitrary other constants that are around. So let's say we have an ax squared y double prime plus bx times y prime plus c x to the 0 times y, the 0th derivative, is equal to 0. So we're going to take a look at the homogeneous version of this and see what kinds of problems or what kinds of results we can get out of this. So if this is our setup, we're going to assume, remember, that your solutions are going to be of the form x to the m power, where x now is a variable. I think m. It would, but we're not creating it. We're not matching the derivative. So if this is x to the n power, where n is the power, n is the number, the order, then it's always going to be x squared for second order, and that's not going to work all the time. Right? If you're saying it's this n right here, then it's always going to be squared for second order. It's always going to be, and it's not going to work like that. All right, let's take derivatives. Y prime is equal to m times x to the m minus 1, and then y double prime is going to be m minus 1 times m times x to the m minus 2. So we have these derivatives. We'll put that in. We get a times x squared. And then our second derivative was, I'm going to reshuffle. So this is our second derivative. And then our first derivative is next to the bx. First derivative is mx to the m minus 1. And then our original function was x to the m. Yeah. And so if we combine all the x's, we're going to have x to the m that we can factor out. And then what do we have left? We have an a, m, x, not x, let's just say m minus 1. So that's taking care of the first term. The second term is b, m. And then x times x to the m minus 1 is x to the m. That gets taken out, plus c is equal to 0. So we're trying to solve for m in this case to find powers that would work for a power function and make this a solution. And so we ignore the x to the m, and then we get this a m minus 1 plus b m plus c equal to 0. This is going to be our new, for the Cauchy Euler equation, our new auxiliary equation. So we had an auxiliary equation for the other types of differential equation, the constant coefficient ones, but now for the Cauchy Euler, we have a slightly different auxiliary equation. And it's not as nice and straightforward, but it still should be simple enough to solve. So we can go from here and then Make it into, yeah, it's going to be a quadratic, right? So from here, let's am squared minus am plus bm plus c equals 0. So am squared plus b minus am plus c equals 0. And so you can go back and use the quadratic formula, and then we'll come up with those three possibilities again. So negative b, so b minus a negative. Let's just go back to a minus b. Plus or minus the square root of b squared minus 4ac divided by 2a. And then if you get two distinct solutions, then your solution is going to be x to the whatever those two distinct solutions are. If you get one repeated root, then we have to use the reduction of order process to find our second solution. And then if we have complex roots, we have to, somehow adjust for that. Sure. So when your equation looks like this, it has an x to the some power that matches the order of whatever it's being multiplied by. Well, let me just give you the results. So the first type of result is obvious. I mean, we were looking for two solutions, and the solutions have to be linearly independent. So we get two distinct real roots, then we get two distinct solutions that are linearly independent. The second case is when we have a repeated real root. When we do that, in the past we just multiplied by an x, but since our solution is x to the m, it's not just going to be x to the m times x. And so I encourage you to do the work to find your second solution using 4.2 methods, the reduction of order, to show that if one of your solutions is x to the m, then your other solution is x to the m times ln of x. Extra knowledge for you. Now, if you think that was weird, if you have complex conjugates, then your solution is going to be, your complex conjugates is going to be some alpha plus or minus some beta times I. And so it's going to be x to the alpha times x to the I beta. And so that I beta can translate into an e to something. And that's how you would come up with this weird set of solutions where you have sine and cosine with an ln inside. Okay. So I guess the work is shown here for cases 1 and 3, and so for case 2, you just need to second order. You're always going to get. Yeah. You're guaranteed to have 5 solutions. Yes. Oh yeah, you can always approximate with some numerical value. So you're always going to have as many solutions as the degree of your polynomial. That, by the way, is called the fundamental theorem of algebra, if you want to look it up. Fundamental theorem of algebra says you have a polynomial with real number coefficients, you're guaranteed as many solutions as the degree of the polynomial, counting multiplicity and counting the conjugates for complex numbers. Google it. Fundamental theorem of algebra. It's like fundamental theorem of calculus, right? It's not like that, but there's these fundamental theorems. There's fundamental theorem of arithmetic. You know what that is? I don't know. Fundamental theorem of arithmetic says that you can always factor your real numbers, your integers, into 1 times something, bunch of product of primes, right? 12, what's 12 equal to? 6 times 2, and then 6 is equal to 2. So it's 2 times 2 times 3, all prime numbers. So fundamental theorem of arithmetic says that you can always factor your natural number into product of primes. Anyways, look it up. We have Google now. We have computers on our phones. You can just literally just type it in your phone. You're having a conversation. You're on a date. Just, oh wait, fundamental theorem of algebra says. Good luck. All right, let's do some examples. Oh, look at all these problems to choose from. Pick a number between 1 and 5. Does somebody say 6? What? One between 1 and 5. 5. That's not between 1 and 5. I suppose we should start a new page for our example. All right, you can verify this is a Cauchy-Euler equation. You got x squared times y double prime. The power of the polynomial matches the degree or the derivative, and then x times y prime, and then 4 times y. So this is in fact Cauchy-Euler. And then we want to look for, so let y equal x to the m, y equal x to the m be the solution. And we'll need a couple of derivatives to get there. Y prime is equal to m x to the m minus 1, and y double prime is equal to m minus 1 x to the m minus 2. So you can put that in there. And then we get x squared m minus 1 x to the m minus 2 plus x times m x to the m minus 1 plus 4 times x to the m. And then you collect all the x to the m's. Each term is going to have an x to the m. And then what you have left is your auxiliary equation that you're going to use. M minus 1 plus m plus 4 is equal to 0. So if we take a look at this, we get m squared minus m plus 4. You get m squared plus 4, 0. And here's an example where you have complex conjugates. So m is equal to plus or minus square root of 4, square root of negative 4. So the i's, it's in the i's. And then you have your solutions. You're done. Except I don't have it memorized yet. Something with a sine and cosine. So alpha is 0 plus or minus 2i. So x to the 0, and then you have sine, cosine with ln's. Yeah. So beta is equal to 2. So y, let's just go all the way here. Cosine 2 ln x plus c2 sine 2. I better make sure. Yep, looks good. Yeah. Yep. Yep. If alpha was a number, it'll be x of that number times, well, c1 x of that number times cosine of this, and then c2 x of that number cosine of that, sine of that. Okay. Questions? All right, so the auxiliary equations aren't as obvious as the previous types of auxiliary equations. So it's hard for me to look at a problem and say, oh, the solutions are going to be case 1, case 2, or case 3. So let's take another guess and do another example. Let's go up to 10, 1 through 10. Pick a number. Solid guess. 8. All right. Let's go through the process again. We're going to let y equal to m, or x to the m. Y prime is equal to m x to the m minus 1, and y double prime is equal to m minus 1 x to the m minus 2. And then we'll go plug all those things in. So we got x squared m minus 1 x to the m minus 2 plus 3x m x to the m minus 1 minus 4 x to the m. And then we know that x to the m is always going to factor out. We got m squared minus m plus 3m minus 4. And then we got m squared, is that a plus 2? Is this going to be another complex? No. Minus 2 plus or minus the square root of 4 minus 4ac over 2. What's in the root? 20. So let's take a 4 out. It'll be 5. Yeah, 2 root 5, and then the 2's would cancel. So it looks like we have a -1 plus or minus root 5. Oh, is that right? No. Oh. Oh, you were saying it right? Oh, yeah. This is almost like the golden ratio. You guys know what the golden ratio is? 1 plus, yeah. Look it up. So the golden ratio is like the most pleasing sort of proportion to the eye. And there's many different figures for it. So one of them is like the expanding triangle with the spiral inside. That's the golden ratio. Fibonacci is kind of also involved with the golden ratio. But anyways, in college, we would say that the golden ratio, the proportions of a person's height from their head to the floor versus the height of their belly button to the floor is supposed to be close to the golden ratio. So that's a good frat party thing to do. Go. So 1 plus or minus root 5 are just numbers. And so, oops, there's no x in there. And so they just would represent the powers. And these are 2 distinct real roots. They're not complex, they're not repeated, so it's that first case. That would be a non-homogeneous. So yeah, we can do something like that. So we can combine it with a variation of parameters, but not the undetermined coefficients. So the undetermined coefficients only work with constant coefficients. This, the variation of parameters is more general. It can work with something like this. So we'll do that in a minute. Oh, I suppose we could do it now. The A's are constants, but then next to the A's and attach X to some power. So the X to some power, again, this is a specialized type of differential equation. And it's specialized because those power functions, the X to the 1, X to the 2, X to the 3, they're next to the derivatives with the matching derivatives and powers. So it's really specialized, but it's another type of differential equation that now we can solve that's not just the constant coefficients that we've been doing. Yes, the power of x. In the original differential equation, the power of x has to match the derivative that you're taking. Well, you're gonna, if you have an x to the third, then you better hope that you have a y triple prime, because if you don't, then it doesn't fall into this category. Then we'll have to find another method. You have to what? And you have to kill it. I could tell you, but I'll have to kill you. Oh wait, that's different. All right. So solving for the homogeneous differential equation is pretty straightforward. Now, when we want to solve for the non-homogeneous type of differential equation, then we're going to be using what's this? I don't know what this is. When we're solving for a non-homogeneous differential equation, then we're going to try to use the same tactics, same things, and then use variation of parameters. So let's try. What should we try? 20, 21, 20. Let's try 22. So in the variation of parameters, we begin by finding the solutions to the homogeneous differential equation, and then we find the Wronskian and do the other stuff. So that's what we're going to need to do again here. So we'll start off with the homogeneous portion. This one is not so easy. Let's see. X squared y double prime minus 2x y prime 2y is equal to 0. We do our potential solutions. And then we plug it in and we get our auxiliary equation. It's almost nice to just kind of memorize the auxiliary equation, but I think going through this process will kind of instill this idea that, we're just not coming out of the equation out of nowhere. So I think it's good practice to go through these steps. So we're going to get m squared minus m minus 2m plus 2. That would be 3 in the middle, right? M squared minus 3m plus 2. Here's a repeated root. Is it? No. So m minus 2 and m minus 1. So we got our y1 is equal to x, and our y2 is equal to x squared. I think that's right. Is that right? So that's the homogeneous solution to the homogeneous part. And now let's use variation of parameters. And for that, this is what we were just working on earlier. Except here we only have a 2 by 2 matrix. So we got an x and an x squared, a 1 and a 2x. So the whatever you call it of that is So our Wronskian is just x squared. Now we need W1, which is, this is your f of x. So in our first column, we would replace with 0 and x to the fourth e to the x. And then here we have x squared 2x. This is going to be negative x to the sixth e to the x. Is that right? And then our W2 is going to be x and 1 and 0 and x to the fourth e to the x. So that's x to the fifth e to the x. Okay. So our u1 prime is going to be w1 over w negative x to the sixth e to the x divided by x squared negative x to the fourth e to the x. And then our u2 prime is going to be w2 over w x to the fifth e to the x minus x squared so x cubed e to the x. Now we need to find our u without the prime, and we need to integrate minus 4 minus x to the fourth. So this is like integration by parts or something, right? Something with a x, I don't know, e to the x squared. So I was tutoring somebody in high school, and then they showed me this little trick for, so this is an integration by parts probably multiple times, right? Have to use u and dv, and it'll reduce. So I saw this column of things that you would write down their information. You would put the u here, the original u, and then you would take the derivative of it like as many times until it disappears. And then you would put your original dv, and then you would take the antiderivative of that as many times as you need to. Have you guys seen this? Watch this. It's kind of cool. Minus 4 x to the third minus 12 x squared minus 24 x minus 24. And then eventually it'll stop. And then you have the derivative of e to the x, just e to the x itself, or the antiderivative. And so when you do integration by parts several times, you get this uv minus v du, and then you would do it again, uv minus v du. So you just combine the u's and the v's for every step. Like here, I have a negative 4 or negative x to the fourth e to the x. And then you'll switch signs. And then you'll switch signs again. Did I miss that one? And then switch signs. And then switch signs. And then there's nothing left, so it's 0. So this is integration by parts 1, 2, 3, 4 times. Is it cool or what? Is this one of those pen drop moments? So that's your integral, that's your first function. Of course, we can, factor out an e to the x if we want, but we'll just leave it like that. So we could do the same trick over here for u2. We're integrating x cubed e to the x dx. So u's and v's, you got x cubed, 3x squared, 6x, and 6, and 0 after that. E to the x, e to the x, e to the x, e to the x. So we start off with a positive x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x. Yeah. Yeah, so this is technically our dv, e to the x right here. So it's uv minus v du, and then another uv minus v du. The order from the first column, yeah, and then one down in the second column. Yeah. Yeah, you're essentially doing integration by parts. Right. Right. So we got our solutions, and so we could just string them all together. I do my general solutions in red. So remember that we have our general solutions that come from here. We have an x and x squared, so c1 times x plus c2 times x squared. Now, also remember that these have to be multiplied by your original solution. So we have an x times this whole big mess. And then again, you can simplify this, make it look a little nicer, but I'll just write it the way it is. So this is a minus x to the fourth e to the x. E to the x is happening in all places. So I will factor out an e to the x. And then I have a minus x to the fourth minus 4x to the third minus 12x squared minus 24x minus 24. And then I have this other one that gets multiplied by x squared, and they all also have an x or e to the x in them. So that's an x cubed minus 3x squared plus 6x minus 6. Okay. Yeah, I don't know. I can't come up with one off the top of my head. I just been thinking about the springs with constant coefficients and stuff. I mean, these do model something. I just don't know off the top of my head. I did find a spring example, not just a picture. So there's a spring here, and you're measuring the distance from the middle. And then there's this round black thing is like the external force. And so let's see, let's make the forcing amplitude smaller and the forcing frequency a little smaller. And so the force is moving the spring, and then the spring has its own motion without the force. And so the red graph is the force. The red sine wave down there is the force. And as the force is moving, the green mass that's being moved around, that distance is being measured by the black graph in here. And so we're going to talk about this after spring break, but you know, this is your standard application for the spring. Okay. The black graph that's here, that is the motion of this green mass with respect to this red 0. The red is where the 0 is. And so we can have more damping or less damping. Damping is like the friction that you have. The spring constant tells you how sturdy or how strong your spring is. The initial position is where it all starts. So we can have the initial position start from the origin. We can mess around with the spring constant. And then we can get rid of the friction. And then we can also get rid of the force, just to see how this would look like. So here, there's not much force happening. So this is just oscillating. And with some damping friction, a little bit of damping friction, this thing is eventually going to get smaller and smaller, the movement. So yeah, I'll post this. This is a CDF file. It's a Mathematica type of file that you can mess around with if you have if you download the CDF player from Wolfram. All right. Anyways, I'll see if I can dig up an example of a Koshi Euler. So these Cauchy Euler equations can go to the higher dimensions also, and so let's do 1/3 or 4th. Let's do number 17. That looks like it might be easy enough to factor. I don't know. It's probably going to be hard. So this thing's not just restricted to second order differential equations. We can go to higher order differential equations. And we're looking at the solutions to the auxiliary equation and the forms of the solutions based on the auxiliary equation. And so I think that's the most important part to get out of this. So let's find our auxiliary equation. So this time you can't just memorize the auxiliary equation that we came up with, because that's only for second order, and this is a fourth order. Oh, wait a minute. I don't want to do this one because it doesn't match. You'd have to do what Nate was saying. You have to integrate this like 3 times and then. Yeah, but it's not a good example. Yeah. You could do that too. And it seems like it's, yeah, let's find another one. What? Because it's not a Cauchy Euler equation from the beginning. So there's 2 options here. One, we can integrate, or we can, like Michael said, we can multiply everything by x cubed. You know, let's do that. All right, let's do it. So it's not Cauchy Euler, but if you multiply both sides by x cubed, this would be x to the 4th, y the 4th derivative, plus 6x cubed, and then this is y to the 3rd derivative is equal to 0. So now it's Cauchy Euler. So it wasn't before. Right. So now that we know this, we can do stuff. What are we going to do? Oh, auxiliary. So we're going to assume that your solution is x to the m, and we're going to need 4 derivatives. So let's take 4 derivatives. The first derivative is mx to the m minus 1. Second derivative is going to be m minus 1, x to the m minus 2. Third derivative is going to be m minus 1, minus 2, x to the m minus 3. And then the fourth derivative is all that stuff with an m minus 3. And then we have x to the m minus 4. All right, so we need the third and fourth derivatives put in here. We got x to the fourth. And then we have this big mess, m minus 1, m minus 2, m minus 3, x to the m minus 4, plus 6, m minus 1, m minus 2, x to the m minus 3. And then they all have x to the m that we can take out. m minus 1, m minus 2, m minus 3, plus 6, m minus 1, m minus 2. Yeah. In fact, I'm going to ask Mathematica to find it for me. So I'm just concerned about what's inside the parentheses. You got m minus 1, m minus 2, m minus 3, and then we have plus 6, m minus 1, m minus 2. I think that's it, right? Set that equal to 0. Should be smart enough to figure out that I'm solving for m. And we have 1, 2, 3, 4 distinct solutions. This is a fourth order, right? Fourth order. 1, 2, 3, 4. Yeah. Well, I wanted at least one to be complex and stuff, but I guess we'll go with this. So had you had any combinations where you had a repeated root or you had complex conjugates, then you would insert those other cases here. But here we have all 4 distinct real roots, so we just write it out as x to those powers. Yeah. If the multiplicity is greater than 2, then we just multiply by another ln. So it's this thing. We're going to multiply by ln x, and then the next one will be ln x quantity squared. And then, again, should check with reduction of order. So your solution is going to be c1 x to the negative 3 plus c2 x to the 0 plus c3 x to the first power plus c4 x squared. And that's it. And had this been a non-homogeneous differential equation, then you would have had to do the Wronskian and do variation of parameters over 4 solutions. So you'd be working with 4x4 matrices and stuff. All right. Fun. You guys have a worksheet or something, right? do on Thursday. So I'm only asking you to do like how many? 3 or 4? I was gonna say 2, maybe 3 or 4, 3 or 4, whatever it says in the instructions. And those should be fairly straightforward, right? And so the videos, I'll say the videos will be due like at the beginning of spring break because I'm going to have another worksheet for you over spring break. All right.